All right, welcome to the deep dive. Today we're going to be looking into something that feels as real as like the ground beneath our feet, something we experience every waking moment, and that's time.
Mm.
But what if that ever-present TikTok isn't quite what we think it is?
Yeah.
What if the latest scientific discussions are pointing to a reality
Hmm.
where time, as we perceive it, isn't fundamental, but actually emerges from something deeper?
Right.
Get ready, because we're about to explore some truly mind-bending ideas about the very nature of existence.
Yeah, that's a great way to put it. For centuries, our scientific understanding has rested on this really solid foundation of time as a constant and unwavering flow from the past through the present into the future.
Yeah.
And Isaac Newton, his giant of science, described it as absolute, true, and mathematical time flows equably without relation to anything external. This was the bedrock of classical physics, the framework through which we understood the universe.
Okay, so let's really nail down this Newtonian view for a second.
Yes.
It's what feels intuitively correct,
Right.
right? Time just marches on. It's this steady beat, and events unfold within that progression. It's like a stage where the universe plays out its drama, and everyone experiences that stage, that beat, in the same way.
It's
Everyone's on the same page.
Yeah, it's a very ordered and predictable picture of the universe.
Right.
But then in the early 20th century, along came Einstein, and
Yeah.
our understanding of the universe took a dramatic turn.
Yeah.
This idea of time as this absolute constant really started to crumble.
Yes. Einstein. Suddenly, time wasn't this fixed entity anymore. Tell us about the revolution that he sparked.
Well, with his special theory of relativity, Einstein revealed something truly astonishing. Time isn't universal, it's relative to the observer's motion.
Okay.
So imagine you're watching someone zoom past you in a super fast spaceship,
Okay.
nearing the speed of light.
Right.
For that person on the spaceship, time would actually pass more slowly than it would for you, standing still. This phenomenon is called time dilation, and it was a complete upheaval of Newton's concept of absolute time. What's fascinating here is that time became intrinsically linked with space, forming this four-dimensional fabric we now call space-time.
No.
So the core takeaway for us is time isn't this fixed background. It actually stretches and shrinks depending on how fast you're moving relative to something else.
So the faster you hurtle through space, the slower you journey through time, at least relative to someone who isn't moving as fast. That's still a head-scratcher, even though it's a well-established part of science.
Yeah, exactly.
But Einstein wasn't finished there, was he? He went on to then bring gravity into the picture, warping it even further with the general theory of relativity.
Precisely. General relativity showed us that gravity isn't a force pulling objects together, but rather the curvature of this space-time fabric caused by the presence of mass and energy.
Okay.
And this curvature has a profound effect on the flow of time as well. For example, time actually runs ever so slightly faster in regions of weaker gravitational fields, like high up on a mountain,
Okay.
compared to down in a valley where gravity is a bit stronger.
That's incredible. So my smartwatch would technically tick a minuscule amount faster if I were hiking at a high altitude.
Exactly. And this isn't just some abstract theoretical notion. It has very tangible, real-world consequences. Think about the Global Positioning System, or GPS.
Okay.
The satellites orbiting Earth are moving at high speeds
Right.
and are in a weaker gravitational field than we are on the surface.
Yeah.
Now, according to relativity, the weaker gravity makes their onboard clocks run faster, while their high speed makes them run slower. The net effect is that their clocks run slightly faster than clocks on Earth.
Okay.
If engineers didn't meticulously account for this relativistic time dilation, GPS navigation would be off by as much as 10 kilometers every single day.
Wow.
So while relativity demonstrated that time is relative and intertwined with space, it still treated time as a fundamental dimension within that space-time fabric.
Yeah. Okay, so we've gone from absolute time to relative time. But time was still a basic component of the universe.
Right.
But now we're hearing that quantum mechanics, the physics of the very small, introduces yet another twist in this story.
It does indeed. When we delve into the quantum realm, the world of atoms and subatomic particles, time is often treated in a fundamentally different way compared to relativity. In quantum mechanics, time is typically viewed as a fixed external parameter.
Okay.
It's the stage against which the probabilities of various quantum events unfold and evolve. This is quite a contrast to relativity, where time is dynamic and intimately woven with space. This fundamental difference in how time is handled has been a major source of tension and a significant challenge in trying to unify these two incredibly successful descriptions of the universe.
So these two foundational pillars of modern physics, relativity for the very large and quantum mechanics for the very small, seem to have conflicting roles for time. And now we're venturing into an even more radical idea. That time itself might not even be a fundamental aspect of reality, but something that actually emerges from a deeper level. So where does this mind-bending concept originate?
A crucial piece of this puzzle comes from the truly bizarre phenomena of quantum entanglement.
Okay.
Imagine two microscopic particles linked together in an incredibly deep and fundamental way, such that they share the same fate, no matter how vast the distance separating them.
Okay.
If you measure a specific property of one particle, say its spin, whether it's up or down,
Right.
the other particle will instantaneously exhibit the opposite spin.
That's the spooky action at a distance that
Yeah.
Einstein famously coined, right?
Precisely.
It sounds like something straight out of science fiction, but it's been repeatedly confirmed through experiments.
Exactly. And this instantaneous connection, this correlation that seems to occur faster than light could travel, really challenges our classical understanding of causality. Our everyday experience of cause and effect is so deeply rooted in the idea of events happening in a specific temporal sequence. A happens, then B happens.
Right. Entanglement seems to bypass this.
Okay, so these entangled particles appear to be connected in a way that transcends our usual notions of space and time. So how does this leap from these spooky connections to the idea that time itself might be emergent?
Well, some physicists propose that the very fabric of time might arise from this quantum entanglement. Consider the Page-Wooders mechanism,
Okay.
a concept proposed back in 1983.
All right.
It suggests that within an entangled system, the experience of time can emerge from the correlations between its different components.
Okay.
Essentially, one part of the entangled system can act as a kind of clock,
Right.
and its entanglement with another part gives rise to the perception of the passage of time. And the shocking insight here is that the very ticking of a clock might not be fundamental,
Okay.
but a result of how different parts of the quantum world are intertwined.
So it's like the ticking of a clock in one tiny subsystem only becomes meaningful because it's intrinsically linked and correlated with changes happening in another entangled subsystem. Exactly. And the profound implication of this is that without this fundamental entanglement, the universe at its most basic level might appear completely static, utterly unchanging.
Oh.
This strongly suggests that time isn't a fundamental ingredient of reality, but rather a consequence, an emergent property of these underlying quantum correlations.
That's a truly difficult concept to get my head around. A static, unchanging universe at its deepest level. It feels completely contrary to everything we observe.
Yeah.
How do physicists even begin to reconcile that with the obvious flow of time we all experience?
It is a radical departure from our intuition. And one of the key tools physicists use to explore this is the Wheeler-DeWitt equation in quantum gravity. This is a really important equation in our attempts to create a theory of quantum gravity,
Right.
to understand gravity at the quantum level.
Right.
And one of its most surprising features is the complete absence of time as a variable.
Okay.
It suggests that the universe as a whole might be described by a timeless wave function. In this view, time only emerges when we consider specific, smaller subsystems within the vast universe and examine their relationships and entanglements with each other.
So the constant flow of time that we perceive is almost like an illusion,
Yeah.
a consequence of how different parts of the universe interact and become entangled.
That's the essence of the idea of emergent time.
Right.
And this concept has some really profound implications. It challenges the fundamental separation of space and time that we find in relativity,
Right.
and it offers a potential pathway to bridge the deep divide with quantum mechanics, where time has traditionally been treated as a fixed backdrop.
Right.
It strongly hints at the possibility of a deeper, more fundamental theory of reality, where space-time itself, and therefore time, arises from more basic quantum processes.
Okay.
Theories like string theory and loop quantum gravity are actively exploring these ideas.
Yeah.
String theory, for instance, suggests that time might emerge from the vibrations of fundamental strings, While loop quantum gravity proposes, it arises from the interactions of discrete chunks of spacetime.
Right.
And the Wheeler-DeWitt equation keeps resurfacing as a key piece of this puzzle, pointing towards that possibility of a timeless underlying reality. These are some of the leading theoretical frameworks trying to go beyond our current understanding and potentially explain how space-time itself emerges from something deeper.
This is all incredibly mind-bending stuff.
Yeah.
If time isn't a fundamental aspect of the universe, what does that mean for our understanding of, well, just about everything?
It opens up a cascade of fascinating possibilities and challenges our current understanding on many fronts. In fields like quantum computing and information theory, if time truly originates from quantum correlations, then perhaps by skillfully manipulating these fundamental connections,
Right.
we could discover entirely new and revolutionary ways to process and utilize information
Right.
philosophically.
Yeah.
It profoundly challenges our linear perception of reality as a strict sequence of events unfolding one after another. The concept of a block universe, where all moments in time, past, present, and future, coexist simultaneously, gains significant traction.
Okay.
Our deeply ingrained perception of a distinct and ever-present now might simply be a construct of our minds.
A block universe.
Yeah.
That sounds like something straight out of a science fiction movie.
It does.
The entirety of existence.
Right.
All moments past, present, and future existing at once.
That's the implication.
Wow.
And it's a truly radical shift in perspective. Interestingly, this idea actually resonates with certain interpretations of Einstein's theory of relativity, which also suggests that all points within spacetime are equally real,
Okay.
effectively blurring the lines of a universal now. This emerging understanding of time could also be absolutely crucial in finally achieving the long-sought-after unification of quantum mechanics and general relativity, the two dominant and incredibly successful frameworks of modern physics that have stubbornly resisted being combined into a single, coherent theory.
What about our own personal experience of time?
Yeah.
That undeniable feeling that it's constantly moving forward, the sense of past, present, and future. Does this idea of emergent time offer any insights into our consciousness?
Absolutely. Some compelling theories propose that our brains play a pivotal role in imposing a sense of flow and causality onto what might be, at a fundamental level, a timeless quantum reality.
Okay.
Cutting-edge neuroscience research is revealing how our brains actively organize the constant barrage of sensory inputs to construct a coherent narrative of past experiences, the present moment, and future possibilities.
Great.
This remarkable ability for mental time travel is likely vital for our survival and our ability to plan and learn. But this raises a profound question.
Yeah.
Is our deeply felt perception of time a direct reflection of objective reality as it truly is? Or is it more of a highly sophisticated survival mechanism, an interpretation our brains create?
Oh, yeah.
And if time is indeed an illusion at a fundamental level, what are the implications for core concepts like free will and causality?
Yeah.
If all moments in time coexist, does our subjective sense of making choices in the now become nothing more than an elaborate construct of our minds?
Wow. That takes the philosophical implications to an entirely new and deeply unsettling level. So to try and synthesize this incredible journey into the nature of time, current scientific discussions are fundamentally challenging our deeply ingrained intuition that time is this basic, ever-flowing constant of the universe.
Precisely. The weight of scientific evidence and theoretical exploration increasingly suggests that time, as we consciously experience it, might be an emergent phenomenon, potentially arising from the strange and deeply interconnected world of quantum mechanics,
Right.
with quantum entanglement playing a starring role.
And this isn't just some abstract academic thought experiment, is it?
No, it's not.
This has potentially profound consequences for how we understand the very fabric of reality, the fundamental workings of the cosmos,
Exactly.
and even our own consciousness and our perception of existence. So if time as we experience it is ultimately a construct, what does that truly mean for the fundamental nature of cause and effect?
Right.
And could our understanding of the seemingly simple word now be radically different from how we currently perceive it?
Yeah.
It's certainly a lot to contemplate. Thank you for guiding us through this deep dive into the surprisingly elusive nature of time. And thank you to you, our listener, for embarking on this mind-bending exploration with us. Until our next deep dive, keep those questions burning.